Rightio, so in this next video on the reciprocal trig functions, I'm just going to have a look at evaluating and simplifying, and yeah, we'll see how far we can sort of get into that now. I realized in the last video that I didn't actually finish up the question because I didn't write the domain and range of that last one. So I'm just going to do that quickly. The domain should be given by the interval 0 to 2 pi, excluding the values of pi on 4 and 5 pi on 4. Also, the range in this case should be given by all real numbers. So now it's good. All right, moving on. So evaluate cosec 15 pi on 4. Rightio, so remember that this means 1 over sine of 15 pi on 4. It's one of the nice things is that you're familiar with the diagram, the ASTC, okay? All sine, tan, and cos. So these reciprocal trig functions follow the same rules. They are all positive in the first quadrant, and the sine is positive in the second, only tan is positive in the third, and the cos is positive in the fourth. What this means is that sec is positive in the first and fourth because that's related to cos. Cosec is positive in the first and second because that's related to sine. And cot is positive in the first and third because that's related to tan. Okay, so we're just going to keep that in mind as we go through these questions. Now, cosec of 15 pi on 4. So, firstly, I'm just going to draw a diagram so I can figure out where it actually goes. So, is 4 pi on 4, 8 pi on 4, 12 pi on 4, so 15 pi on 4 should be down there. It's in the fourth quadrant. And we know that sine in the fourth quadrant is negative. So what I can say is that cosec of 15 pi on 4 is equal to negative cosec of pi on 4. These would be equivalent expressions. And cosec of pi on 4, well, that's just going to be 1 over sine of pi on 4. Which, if you know your exact values, sine of pi on 4 is root 2 on 2. So we've got negative 1 over root 2 on 2, which makes it negative 2 over root 2, because we just flipped the fraction, and we can rationalise that denominator to get negative 2 root 2 on 2, which the 2's cancel each other out, and so we just get negative root 2. Now that I think about it, that could have probably been done easier just by saying that it's 1 over root 2 instead of root 2 on 2. Sometimes having the rationalised denominator form isn't the best. Alright, so the next one, cot of 13 pi on 3. Again, need to consider which quadrant this is in. So 3 pi on 3, 6, 9, 12, and then 13 pi on 3 is going to put us up here. So we're in the first quadrant. And so I could say that that's equal to cot of just pi on 3 because cot is going to be positive in the first quadrant. And so that is 1 over tan of pi on 3, which tan of pi on 3 should be root 3. So it's really just 1 over root 3, which if we rationalise that denominator now, we'll get root 3 on 3. Okay. So they can all sort of be done that way. We also get questions like this where we have to simplify algebraic expressions and try to turn them into their nicest form. In order to do these questions, not all of them, but some of them, we need to be aware of some of the trig identities. So firstly, we need to know that tan x is equal to sine x over cos x. We also need to know of the Pythagorean identity, which is sine squared theta plus cos squared theta equals 1. Now we can get different versions of this. If I were to divide both sides by sine theta, I would get 1 plus cot squared theta equals cosec squared theta. Alternatively, if I were to divide both sides by cos squared theta, then I would get tan squared theta plus 1 equals sec squared theta. So three different versions of that Pythagorean identity, and we do need to be able to use them perhaps, we'll just see how that goes. So the first one, cos x plus sin x tan x, we need to just simplify it. So I guess there's a couple of things to this. We need to know like when it's been simplified, so how far we actually need to go with this. What I'd say is that most of these questions are going to work out quite nicely. They tend to come down to just a single term or something like that and be really nice. So to begin with, I'm going to recognize that tan x is the same as sin x over cos x. So I end up with cos x plus sin x times sin x on cos x. Well, this is already not looking too bad. So I've got cos x plus sin squared x over cos x. And I'm noticing now that I've got a sin squared x there. So ideally I want to try and make it cos squared x as well, because together sin squared x and cos squared x will be 1. And it's pretty nice because we have two different parts here, and one of them is a fraction with a denominator of cos x. So I need to make a denominator of cos x for the other one so I can group them together. And when I do that, I'll multiply the cos x by cos x on cos x, which is going to give cos squared x over cos x plus sin squared x over cos x. I could combine these into a single fraction, so cos squared x plus sin squared x all over cos x. And then the Pythagorean identity tells us that cos squared x plus sin squared x is 1. So it's really just 1 over cos x, which is sec x. So I was able to show that cos x plus sin x tan x is really just sec x. As I said, they tend to work out quite nicely. As for the second one, I'm noticing tan squared x and sec squared x, and well, I can see both of those in the third version of the Pythagorean identity that I wrote down. So I'm going to just rearrange this equation right here. And I want to get tan squared theta minus sec squared theta, so I'm going to just subtract sec squared theta on both sides. I'm also going to subtract 1 from both sides. So that should leave me with tan squared x minus sec squared x equals negative 1. And well, that's the answer. That was actually a pretty straightforward one to do. Anyway, that's about all there is to these. You have to, be prepared to jump in the deep end a little bit with these kind of questions. They can sometimes get a little bit tricky, and the advice I'd give is try and get everything in terms of sin and cos if you can. Look for those trig identities, in particular the Pythagorean identities, because they tend to make life fairly good for us. Anyway, I'll leave it there and see you next time.